Hey, what's going on, guys? CodeMonkey here. In this video we're gonna start working on the implementation of the transposition table. So the exact source I'm supposed to be referencing during the next few videos would be this Bruce Moreland's pages, even though there are some questionable things like recording hash within where the evaluation is returned. Well, even assuming that instead of the straight ahead evaluation we return the question search, it's a bit strange to record a hash here. At least I have never seen this in the real world source code of the open source chess engines. And when I asked this question on talkchess.com, Harmgert Miller replied that this is absolutely weird disaster, and as far as the question search is not called, he's not going to actually kind of answering this question because this is all wrong, as he said, just all wrong. Well, another brilliant answer by AJM, which takes me for about 10 years to understand, as always. So I just want to say that I didn't actually do this line in my final implementation of the transposition table, but if we just ignore this line, then everything else seems to be, well, at least working in terms of speeding up the performance. And also I heard that there are some very fancy and cool techniques, like to use the transposition table to speed up your perf test and things like that, but that's rocket science to me, so I'm not going to be even trying to do this, at least at this moment in particular. And what I will try to do is actually to implement the very basic transposition table, just to have a speed up within a search, so the last nodes would be traversed eventually, and the more cutoffs occurring, because we would be referencing the values from the transposition table. And another one important thing to consider before we start, well, usually, like normal chess engine, not CodeMonkey engines like BBC, they usually use so-called dynamic memory allocation. So the idea is that you can set using the set option command from the GUI, you can set the appropriate number of megabytes you would like to have as the size of the transposition table for your engine. And this is really cool, but that's a little bit too complicated for me at the moment. Not in terms that I can implement the dynamic memory allocation in C, but I just don't really want to get disturbed by tracking those possible memory leaks. I don't really like this dynamic memory allocation and trying to avoid this every time I can. So maybe in the further versions this would arrive. But anyway, we will implement the static transposition table array at very first, and then we would actually go and create the functions to actually read and write entries from the transposition table, and then we'll embed this into our search to see how it works. So quite pretty simple and straightforward as always. So without further ado, let's actually go and write some code. So in this video we will only define the transposition table and create a function to clear it. That's kinda it. So I just want to find where my MVV LVA is, and probably just before the move scoring here, I would like to add the transposition table related code. So let's actually go for it. So just where the definitions end, scoring moves, yeah. So right here, I want to have the code for transposition table. Okay, like this, or nope, like this. So let's start with the very definitions. So save. I just grabbed the code from Bruce Moreland and just slightly change it to my own needs. Okay, so I would be trying to explain how it works. Well, assuming that I've learned how it works not very long time ago, and I don't even know even now whether my transposition table actually works correctly or not. Well, it does give some speed up, but I'm not sure if it is bug free. So if any of you guys have an experience with transposition tables, please let me know in the commentaries. I will deeply appreciate your kind points to my weird bugs. Okay, so let's go step by step. So the very first thing Bruce is doing, he's defining the hash flags. So what are the hash flags and what are they needed for? So as far as you know, there are 3 types of moves within the alpha beta search. So we have the moves that fail high, those producing the beta cutoffs, moves that fail low, those that don't increase the alpha, the score of alpha, and so-called PV nodes, so those that actually increase the value of alpha. So when we have the fail low situation, this is known as the hash beta flag. So we're flagging that this is the beta score. In case of if the node fails low, we have the hash alpha flag. But here this is a little trick. This is why, well, in WISE this is implemented using the old alpha variable initialized here in the beginning. So if alpha is not equal to old alpha, in the case he writes the exact score, and otherwise he writes the alpha score. But Bruce does this little trick here, so he initializes the flag at the very beginning, and then so by default it would be the hash alpha. So if it didn't change here, then this hash flag exact would remain hash alpha. And if there was a move increasing our alpha, in this case this hash flag would be a flag exact. So hash flag beta pointing out that this is the beta score, hash flag alpha pointing out this is the alpha score, and hash flag exact means that we have the exact evaluation, not the alpha bound or the beta bound, but the exact score returned from our search. So that's another flag. So these 3 flags are kind of three types that we would be later on making use of while probing the transposition table entry. So hope that's clear. Then he creates this structure. Well, I have no idea why to give a name here. I never do this. Probably that's weird and not the way to do, but I'm trying not to do what I don't understand. And also I would like to call this variable type as TT, which means transposition table. And generally this is the transposition table data structure. Okay, here we have the transposition table hash flags. Okay, sorry guys, just okay, it would be better now. So it's a bit cold outside, that's why I'm wearing a coat now. Okay, so I would like to call this hash flag exact. That's, by the way, that's where I started when initially was learning from WISE series. The way what I was doing, I was just following the tutorial while changing the name of the variables at the same time, and if I could get the same result as was in the video, I was really happy. So hash flag exact, hash flag alpha, that's the CodeMonkeyKing's way to learn new things. Hash flag, just change the variable names and grab the code, and have hash flag beta. Okay, so flag exact, flag alpha, flag beta. So these are just the constants to consider. And now the inner key, the inner fields within this structure. So key, this actually means the hash key. So that unique, almost unique chess position identifier. Okay, so here we have the current search depth, so this would remain the same. Flags, well, better just call it flag, because it would be matching one of these flags. So which flag? So flag, the type of node or move. Well, actually, when I was once pointed out that node is actually not a move. It's better to call the node is a position, but I was using this move every time, so that's probably not the best ever idea. So I don't know, maybe I changed that one day. But according to the correct terminology, node is considered to be the position and not the move. But I call it move because, yeah, probably because I'm Monkey keen. Okay, so flag the type of node, and I just specify the type. So it may be the fail high, which means score is greater or equals than beta. It might be fail low, which means that score is less than alpha. Well, probably we can say even less equals than alpha, because if it doesn't increase the alpha, it still kind of fails low, right? And also PV, principal variation node, with the condition of score is actually greater than alpha. So it's a little bit too, well, I hope this is clear, like what this fail low, fail high means. Just probably get rid of them better. I've been explaining this, so and also this is explained very good on Bruce Moreland's pages in the section of principal variation search, so feel free to examine this. So if you just go up, and I'll probably just put a link into the description to make it even more clear. So principal variation search, where are you, man? Principal variation search. So here we have this definition of 3 types of nodes in the alpha beta, which is very essential and very basic. Okay, so I didn't know this for years, guys, and that's the reason why it was incredibly hard for me to make use of the answers from Talk Chess forum when you don't know what this fail high, fail low means. So this is a must-know thing, must-learn thing. Okay, so value is what we Monkey Kings call score within our source code, and so score, and this might be actually respectively to this guy. So fail high, this might be a beta. Well, actually, let's start with a fail low. It's more traditional. So fail low and fail high and PV. So this might be the alpha score, the beta score, and the principal variation node or move, or it's better to say the position score. Okay, so also there is a good idea to keep to store the best move in the transposition table, and there is the vast majority of cases how you can make use of this later. An example trying to extract the principal variation out of transposition table, and probably that is it. But I'm not gonna be using this because I'm not really that sure that my implementation is correct, so I don't really want to rely on something that I'm not 100% sure within. I mean, the current implementation, at least, well, it seems like it doesn't break anything, and it does the engine performance slightly better, so that's the reason why I keep it, and that's the field for the further research within the transposition tables field. But I don't really want to rely on it, And before I started learning this, I was thinking like to extract the position repetitions using this hash key from the transposition table, but I'm not yet sure if I'm still about to follow that approach, because I don't really trust my own implementation of transposition tables. So I will probably go some other way. But anyway, well, I know, guys, it's probably sounds a bit weird. Like, why the hell am I making the tutorial if I'm not sure 100% in my implementation? Well, that's because I just want to show you the way how I learn things, and that's because that it actually does improve the performance slightly a bit. So that's the reason for doing this. For those of you wondering like, why the hell is this happening? Probably like this would be just fine. Okay, and so I guess this is it, right? And the very last but not least variable, the constant to define, is actually the hash table size. So I want to define hash size like this, and I would be using the hexadecimal value. So a megabyte in hexadecimal, let me just show you the calculator to give you an idea where I'm this taken from. So in hexadecimal, this is 1 and 5 zeros. In decimal, this is 1 megabyte in bytes. So 1, 2, 3, 4, 5, and I would be using up to 4 megabytes as the default value for my transposition table. So that's kind of it. Again, like normal people doing this by dynamically allocating the memory for to serve the purpose of storing the transposition table, but CodeMonkey like me would do this statically, at least in the very initial version of BBC. So now when we have our size, yeah, now we can actually go for, so the next thing to consider, well, we again, assuming the static implementation, I will define the transposition table structure instance just right now globally, while when it comes to the dynamic memory allocation, obviously it would be done a different way. So, but at this moment I want to define transposition table. I just call it TT. I hope this is quite pretty clear. So let's make it like this. Define transposition table structure instance. It's a type def struct, but well, let's say transposition table instance like this. So it would be TT, and just call it transposition table, and the size would be hash size like this, hash size. Okay, now another thing to consider, so if we have a global variable like without outside a structured simple integer or whatever, another variable, if it's not if no value is assigned to that variable by default, assuming the GCC compiler in C programming language, that variable would be initialized to 0. But in case when we're dealing with the structures, so these variables are not gonna be are not gonna be initialized to zeros by default. So we need to do that explicitly. So here, well, actually, this is the initialization, but I would like to call this like clear hash table, because one of the other disasters within the current version I'm working with is if I don't clear the hash table every iteration, no, not every iteration, every time I'm searching for a new move, every new search, if I don't clear the hash table, I'm getting a weird results, and I don't know yet the reason for that. So if someone of you guys knows that, please let me know in the commentaries. I would be really happy to learn like why the hell is that going on, basically. Well, anyway, so I want to create the void function called clear transposition table, and here, so we need to loop over overall the elements over transposition table elements. So I can simply say for int, well, let's call this index basically. Index is equal to 0, index is less than the hash size, this constant, the hash size of 4 megabytes that we've default this, hard-coded this constant, and index plus plus. So, and here we want to initialize every element. So okay, I think now it's time to compile and run the code. So make debug, and if it compiles, I want to run the BBC binary executable. Okay, I don't really want the perf test to be running here, so let's do it again. So I don't yet, well, yeah, let's actually, I didn't yet call this function, so let's call this clear hash table. Okay, so we're not gonna see any output, I believe, because there is nothing much to see but 0 elements. Okay, so clear hash table, clear, oh, hold on a sec. Okay, I call it hash table here, but there I call it a transposition table. So what name is better? Hash table or transposition table? Oh my god, naming variables is the toughest part in programming for me personally. Okay, transposition table. Well, let's skip it. As far as we call it TT, let's skip it transposition table. Yeah, so in order to avoid any confusion, let's leave this as the transposition table. So it's a bit too long, but at least clear what do we reference in particular. So clear transposition table. Well, actually, this is also known what is the hash table. Let's call it TT, and in parentheses, like, this is the hash table. Okay, so, and now we need to reference, oh my god, I forgot how to do this. We need to reference every, so transposition table indexed by the index, right? Okay, and now all the elements, so the hash key. As far as I'm not working with the pointer, I don't know if it gives me an error, so let's see. Hash table equals to 0. Okay, let's have a look if it works. Yeah, so if I was working with the pointer, like we'll usually adding the pointer here, like TT pointer to transposition table, in that case it would be this like definition. But if we're just working with a global variable, the notation is to place this dot, because it's not a pointer. It's, well, it is a pointer technically, but from the C programming language syntax perspective, there should be a dot. And now we need to initialize all the fields available. So the second would be the depth, and then the flag, and then the score, and that's it. Okay. Okay, so here we want to reset TT inner fields. Okay, and I guess this is it basically. I really guess this is kind of it. Okay guys, just let me quickly check this out and I'll be back in a moment. Yeah, it seems like it's working, so yeah, let's compile and run the code to make sure it compiles and runs again, so it won't happen like in one of the previous videos. Okay, and yeah, nothing really to show in the console now because we're not really doing much other but initializing this array, this transposition table array. So just to summarize, so we're defining the array of elements of where every element is this kind of like structure. So it has, every element has the hash key, depth, flag, and score. These are the exact items we're supposed to be writing data to and reading data from. Within the next two functions serving the purpose of storing the hash entry and actually reading the hash entry. And again, like this naming is a little bit because those functions would be named like store hash entry and read hash entry or something. It's too long to say set transposition table entry, so I will probably now make it well, transposition table. So well, okay, I keep the type, but I just call this hash table like this. Hash table, just to give it a nice size. So transposition table, let's say aka hash table. So I just leave this definition of TT because I like how it looks like. And here let's call this transposition table instance. So hash table. So I hope this is clear. So this hash table is literally our transposition table. Now let's call this one clear hash table, and at the very end we also call this clear hash table. So let's make sure it still compiles and runs. Oh, okay, and obviously I just need to make it like this. Yeah, transposition table is a bit too long variable name. Okay. Yeah, now I really like it. Okay, so TT just is like an integer, just the data type, shortened from transposition table, and the hash table is actually the variable name for this array. Well, okay guys, so I hope this is clear, and the next couple of videos, well, probably I would have been shortened this to the only video to actually read and write entries from the transposition table, and then the video after that we would be embedding our transposition table into a search to see the performance grow. So this is it from my side. I hope you learned something interesting out of this tutorial. Hope to see you in the next parts. Until that time, and take care.